Grounding and bonding are two distinct but related concepts in electrical systems that ensure safety and proper operation. Grounding connects the non-current carrying metal parts of an electrical system, for example, equipment enclosures and frames, to the ground. Grounding creates a low resistance path for electrical current to flow to the earth in the event of a fault. Grounding protects people and equipment from electrical shocks by diverting current away from them. Bonding connects metal parts within an electrical system, such as conduit, cable trays, and metal boxes, to each other to provide a continuous path for current to flow. Bonding ensures that all metal parts are at the same electrical potential, eliminating potential differences that could cause arcing or shocks. Bonding enhances the effectiveness of grounding by providing a low resistance path for fault currents to reach the grounding electrode. Grounding and bonding are related because bonding helps to ensure proper grounding. By connecting metal parts together, bonding reduces the chances of static electricity buildup and increases the flow of current to the grounding electrode during a fault. The main difference between grounding and bonding is their purpose. Grounding protects against electrical shock by connecting metal parts to the earth. Bonding ensures a continuous path for current flow and eliminates potential differences within the electrical system. Grounding is the connection of a conductive part to the ground or to a conducting body that is in direct contact with the earth. Bonding is the permanent joining of metallic parts to form an electrically conductive path that ensures the electrical continuity of the connected parts. Let's delve into grounding further. The purpose of grounding is primarily safety. It provides a path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly trip and energize the circuit. This prevents dangerous voltages from appearing on metal parts that could be touched, reducing the risk of electric shock. Grounding also helps to stabilize voltage during normal operation, reducing electrical noise and improving the performance of sensitive electronic equipment. There are several types of grounding. Firstly, system grounding, which connects the neutral point of a power system to earth. This is common in alternating current systems. Secondly, equipment grounding, which connects the non-current carrying metal parts of equipment to earth. This is the type most people think of when they hear the term grounding. The components of a grounding system include the grounding electrode, which is a conductor buried in the earth to provide a connection to ground. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The grounding electrode conductor connects the grounding electrode to the electrical system. This conductor must be sized appropriately to handle the maximum fault current. The equipment grounding conductor connects the non-current carrying metal parts of equipment to the grounding system. This conductor provides a low impedance path for fault current to flow back to the source. Now let's shift focus to bonding. The primary goal of bonding is to create an equipotential plane, meaning that all metal parts within the electrical system are at the same voltage. This eliminates potential differences that could cause arcing or electric shock. Bonding also reduces electromagnetic interference, or EMI, by providing a low impedance path for high-frequency currents to flow. Several types of bonding exist. Firstly, equipment bonding, which connects the non-current carrying metal parts of equipment together. Secondly, structural steel bonding, which connects the metal frame of a building to the grounding system. Thirdly, concrete encased electrode, also known as a U for ground, which is a grounding electrode encased in concrete. The components of a bonding system includes bonding jumpers, which are short conductors used to connect metal parts together. Bonding bushings provide a connection between metal conduit and equipment enclosures. Bonding lock nuts are used to connect metal conduit to metal boxes. Now, to further clarify the relationship between grounding and bonding, consider this. Bonding ensures that all metal parts are electrically connected, providing a continuous path for fault current. Grounding provides a path for the fault current to return to the source, tripping the overcurrent protection device. Without bonding, fault current may not have a low impedance path to ground, potentially leaving metal parts energized and creating a shock hazard. Bonding enhances the effectiveness of grounding by providing multiple paths for fault current to flow. This reduces the impedance of the grounding path and ensures that fault currents are quickly cleared. Now, let's emphasize the key differences between grounding and bonding. The purpose of grounding is to provide a path for fault current to return to the source and protect against electric shock. The purpose of bonding is to create an equipotential plane and eliminate potential differences. Grounding connects metal parts to the earth, while bonding connects metal parts to each other. Grounding uses a grounding electrode to connect to the earth, while bonding uses bonding jumpers and other connectors to connect metal parts together. In summary, grounding and bonding are two essential components of a safe and effective electrical system. Grounding provides a path for fault current to return to the source, while bonding creates an equipotential plane. Both grounding and bonding are necessary to protect people and equipment from electric shock. To ensure proper grounding and bonding, several best practices should be followed. Firstly, use appropriately sized conductors for grounding and bonding. The size of the conductors should be based on the size of the circuit and the potential fault current. Secondly, make sure that all connections are clean and tight. Loose or corroded connections can increase the impedance of the grounding path and reduce its effectiveness. Thirdly, follow all applicable codes and standards. The National Electrical Code or NEC provides detailed requirements for grounding and bonding electrical systems. Fourthly, inspect and test grounding and bonding systems regularly. This will help to identify any problems and ensure that the system is functioning properly. This would include visual inspections, continuity testing, and ground impedance testing. Visual inspections involve checking for loose connections, corrosion, and other signs of damage. Continuity testing verifies that there is a continuous low impedance path between all metal parts. Ground impedance testing measures the impedance of the grounding path to ensure that it is low enough to allow fault currents to flow quickly. Now let's consider some common misconceptions about grounding and bonding. One common misconception is that grounding is only necessary for sensitive electronic equipment. In reality, grounding is necessary for all electrical systems to protect against electric shock. Another misconception is that bonding is only necessary in hazardous locations. While bonding is particularly important in hazardous locations, it is also necessary in other locations to prevent static electricity buildup and reduce electromagnetic interference. Another misconception is that a ground rod is all that is needed for proper grounding. While a ground rod is an important component of a grounding system, it is not sufficient on its own. A complete grounding system includes a grounding electrode, a grounding electrode conductor, and an equipment grounding conductor. Another misconception is that bonding is simply a matter of connecting all metal parts together with any available wire. Proper bonding requires using appropriately sized conductors and making sure that all connections are clean and tight. The NEC provides specific requirements for bonding different types of metal parts. Grounding and bonding are critical for electrical safety and are addressed extensively in the NEC. Article 250 of the NEC covers grounding and bonding requirements for electrical systems. This article provides detailed information on grounding electrodes, grounding electrode conductors, equipment grounding conductors, and bonding requirements. Some key sections within Article 250 include 250.4, which covers general requirements for grounding and bonding. 250.24 covers grounding of service-supplied alternating current systems. 250.30 covers grounding of separately derived alternating current systems. 250.50 covers grounding electrode systems. 250.92 covers bonding of equipment containing over 250 volts to ground. Understanding and following the requirements in Article 250 is essential for ensuring the safety of electrical systems. In addition to the NEC, other standards and regulations may apply to grounding and bonding, depending on the specific application and location. These standards may be developed by organizations such as the Institute of Electrical and Electronics Engineers or IEE, the National Fire Protection Association or NFPA, and Underwriters Laboratories or UL. It is important to be aware of all applicable standards and regulations and to follow them carefully. Proper grounding and bonding are essential for protecting people and equipment from electrical hazards. By understanding the principles of grounding and bonding and following best practices, you can help to ensure the safety of electrical systems. Regular inspection and testing of grounding and bonding systems are critical for identifying and correcting any problems. If you are not qualified to inspect and test grounding and bonding systems, it is important to hire a qualified electrician to do so. Remember, electrical work can be dangerous, and it is always best to err on the side of safety. Let's consider some specific examples of how grounding and bonding are applied in different situations. In a residential wiring system, the grounding electrode is typically a ground rod or a metal water pipe. The equipment grounding conductor is typically a green or bare copper wire that runs with the circuit conductors and connects to the metal enclosures of electrical equipment. The bonding jumpers are used to connect metal water pipes, gas pipes, and other metal parts to the grounding system. In a commercial building, the grounding system may be more complex and may include multiple grounding electrodes such as ground rods, ground plates, and concrete encased electrodes. The equipment grounding conductors may be run in conduit or cable trays. The bonding jumpers are used to connect all metal parts to the grounding system, including metal conduit, cable trays, metal boxes, and structural steel. In an industrial facility, the grounding system may be even more complex and may include specialized grounding techniques to protect sensitive electronic equipment from electrical noise. The equipment grounding conductors may be run in dedicated grounding conduits. The bonding jumpers are used to connect all metal parts to the grounding system, including machinery, equipment, and structural steel. Let's consider some common grounding and bonding mistakes to avoid. One common mistake is to use undersized conductors for grounding and bonding. The size of the conductors should be based on the size of the circuits and the potential fault current. Another common mistake is to make loose or corroded connections. Loose or corroded connections can increase the impedance of the grounding path and reduce its effectiveness. Another common mistake is to fail to bond metal water pipes and gas pipes to the grounding system. Metal water pipes and gas pipes can become energized if they are not properly bonded. Another common mistake is to use the neutral conductor as the equipment grounding conductor. The neutral conductor is designed to carry normal load current, and it should not be used as the equipment grounding conductor. Another common mistake is to fail to properly ground separately derived systems, such as generators and transformers. Separately derived systems must be grounded in accordance with the NEC. Let's consider some advanced grounding and bonding techniques. One advanced technique is to use isolated grounding systems for sensitive electronic equipment. Isolated grounding systems use a separate grounding conductor that is isolated from the building's main grounding system. This can help to reduce electrical noise and improve the performance of sensitive equipment. Another advanced technique is to use equipotential bonding grids in areas where there is a high risk of electric shock, such as swimming pools and spas. Equipotential bonding grids are made of interconnected copper conductors that are buried in the ground. They provide a low impedance path for fault current to flow, reducing the risk of electric shock. Another advanced technique is to use surge protection devices or SPD to protect electrical equipment from voltage surges. SPD are designed to divert surge current to ground, preventing damage to equipment. When troubleshooting grounding and bonding problems, it's crucial to follow a systematic approach. Firstly, visually inspect all grounding and bonding connections for looseness, corrosion, or damage. Secondly, use a multimeter to verify continuity between all metal parts and the grounding electrode. Thirdly, use a ground impedance tester to measure the impedance of the grounding path. Fourthly, check for voltage between metal parts and ground. If there is voltage present, it indicates a grounding problem. Fifthly, consult the NEC and other applicable standards to ensure that the grounding and bonding system is in compliance. Effective grounding and bonding are not one-time installations, but rather ongoing responsibilities. Regular maintenance is essential to ensure that the system continues to function properly. This includes periodic visual inspections, tightening of connections, and testing of the grounding impedance. It also includes keeping the grounding electrode free from corrosion and ensuring that it is properly buried in the earth. Documenting grounding and bonding systems is crucial for future reference and troubleshooting. This documentation should include a wiring diagram showing the location of all grounding and bonding conductors, a list of all grounding electrodes and their locations, and a record of all inspections and tests. This documentation should be kept in a safe and accessible location. Continuing education is essential for staying up to date on the latest grounding and bonding techniques and requirements. The NEC is updated every 3 years, and it is important to stay informed of the changes. There are also many training courses and workshops available on grounding and bonding. Taking these courses can help you to improve your knowledge and skills and ensure that you are providing safe and effective grounding and bonding systems.